So good afternoon, and thank you for attending our webinar, CUI Research, the Critical Components and Findings. My name is Ames Kulprathipanja with Johns Manville, and I will be your co-host today along with Leo Caseres from Southwest Research Institute. Before we get started, I would like to cover 3 procedural items. First is to let you know that we'll be doing a Q&A at the end of the presentation. If you have any questions throughout the webinar, please use the questions box in the menu to the right of your screen to submit your questions. My colleague Kim Melton will be monitoring your questions as they come through, and we'll address them at the conclusion of our presentation. Second, all attendees today will receive a certificate of completion following the webinar. Kim will give you more details about the certification after the presentation. Finally, at the end of the webinar, there will be a survey. If you have any comments or suggestions on anything that we can do better, we kindly invite you to fill out the survey so that we can continue to improve the webinar content in the future. So now for some introductions. My co-host today again is Leo Caseres. Leo, can you please introduce yourself and Southwest Research Institute?
Thanks, Ames, for the introduction. Again, my name is Leo Caseres, and I'm a senior research engineer in the Mechanical Engineering Division at Southwest Research Institute for almost 10 years. I earned my bachelor degree in chemical engineering from the University of Buenos Aires in Argentina, and a master's and Ph.D. in civil and environmental engineering from the University of South Florida in Tampa. In my capacity as Southwest Research, I have been involved in the areas of corrosion control, monitoring, and prevention, coding performance evaluation for a wide variety of applications, including CUI evaluation. For those not familiar with Southwest Research Institute, the Institute, headquartered in San Antonio, Texas, is one of the oldest and largest independent nonprofit applied research and development organizations in the United States. Since its inception in 1947, the Institute holds more than 1,200 patents and has earned the prestigious R&D award 41 times. During the last year only, Southwest Research Institute published over 600 technical papers, made over 600 presentations around the world, granted 60 invention disclosures, and received more than 45 patents awards. Now I'll go back to you, Ames, for your introduction. Thank you.
Thanks, Leo. Again, my name is Ames Kulprathipanja. I've been with Johns Manville for over 10 years and have worked in a number of capacities in the building installations, performance materials, OEM, and industrial business units. I'm currently the innovation leader within the Installation Systems Division. I earned my bachelor's degree from Iowa State University and Ph.D. from the University of Colorado Boulder, both in chemical engineering. So at Johns Manville, we live by 4 pillars, which we call the JM experience. These 4 pillars include people, passion, perform, and protect. These webinars are an example of how we share the pillars with our customers and market influencers. Our goal of these webinars is to provide an educational tool for you and your company. So with that in mind, I'd like to reiterate, like I did in the beginning, if there are any questions or suggestions on how we can improve the JM experience for you, we kindly invite you to please fill out the survey at the end of the webinar so that we can address them in the future. Okay, so to kick off the technical portion of the webinar, Leo will be starting with some background on CUI and test methods to evaluate CUI. Leo?
Thanks, Ames. CUI background. Let me start by saying that corrosion under insulation, or CUI for simplicity, represents a severe threat to the on-stream reliability of many of today's refining, chemical, power generating, and pulp and paper industries, including onshore and offshore installations. In practice, CUI commonly appears in the temperature range between 50 degrees Fahrenheit and 350 degrees Fahrenheit, and where there's a cyclic operation of the equipment. For carbon steels, CUI manifests in the form of uniform and localized corrosion. For austenitic stainless steels, CUI is normally localized, leading to stress corrosion cracking if appropriate environmental conditions and stress levels are met. The effects of corrosion under insulation can be very severe. It can lead to sudden and catastrophic failure, especially in systems that operate at high temperatures and pressures. Variables in CUI processes. There are a great number of variables that are associated with the CUI processes. Examples of these variables include moisture, oxygen availability, metal temperature, type of CUI preventing coatings, and insulations. There can be various contaminants on the surface of the jacketing, and these contaminants can be picked up and carried into the insulation when the water enters the system. Chloride concentrations less than 10 parts per million are enough to cause stress corrosion cracking in stainless steel pipes operating above 140 degrees Fahrenheit. Pipes which operate at the range of CUI temperatures can have a repeated cycles of condensation and re-evaporation, resulting in a more aggressive form of corrosion. With these slides, I want to emphasize that CUI scenario is pretty complex. The great number of variables may have a synergistic effect on the development of CUI. That is why CUI has to be viewed as a system approach, as mentioned in numerous standard practices and guidance documents. Mechanisms of CUI. The mechanism of CUI is initiated by the ingress of external solution into the thermal insulation, which traps the solution at the annular space between the metal surface and the insulation. Just for the record, the true cause of CUI is due to long durations of contact with wet insulation, not just the lack of proper coating, for instance. We cannot rely on a coating to be the ultimate answer for CUI prevention. We have to rely on the knowledge that what really causes CUI is long-term water contact, so careful design and material selections are important in mitigating CUI. Impact and cost of CUI. An Ames study back in 2002 estimates that the annual cost of corrosion in production manufacturing in the United States to be around $17.6 billion, out of which 34%, or about $6 billion, is associated with the pulp and paper industries, and 40%, or $6.8 billion, is related to the oil and gas industries. According to a study presented to the European Federation of Corrosion, the following conclusions were extracted from that investigation. The highest incidence of leaks in refining and chemical industries are due to CUI and not to process corrosion. Over 80% of most piping leaks occurs in diameter less than 4 inches. Between 40 and 60% of piping maintenance costs are related to CUI, according to the next study back in 1992. And last, CUI is associated with the most lengthy refinery downtimes. As such, this type of corrosion can be serious problems and even catastrophic consequences in areas that are not normally of a primary concern to an inspection program, causing adverse economic losses in terms of downtime and repairs. Need for CUI testing. The current standards related to CUI are either difficult to use or in many cases lack of relevancy. Coating and insulation vendors started to use internal test methods to evaluate CUI performance at elevated temperatures. The main issue with those tests is that in some cases the test method is so aggressive that systems which have performed in the field for years suddenly look really bad in the lab and vice versa. The next SP0198 document offers a true view of CUI mechanisms, as well as directions on coating systems and the limitations of certain coating technologies. Available CUI test protocols. Experience has shown that performance-based qualification of coatings and insulations are more effective at raising performance rather than compositional standards. The majority of the CUI test methods are not field validated, plus there are either some geometrical issues of the test specimens or temperature limitations, in addition to the lack of insulation in the tests. All that may pose real problems when it comes to mimic CUI in the laboratory. Recently, ExxonMobil partnered with CUI Research Institute to develop a test method to better assess CUI. The resulting test method reproduced field observations very well in terms of coating performance and corrosion rate of bare metals. One of the main benefits of the test protocol is that it is not a pass-fail type approach. Instead, this test protocol is to be used as a means of establishing the relative performance of coatings and insulations given a set test criteria. The test method allows for various CUI environments that ranges from isothermal to cyclic operations. I will explain the developed test approach more in detail later on, and I will refer this test method as the NACE TG516. Next, I'm going to address the NACE TG516 test protocol for CUI evaluation. The design of the test method is based on an approach that simulates CUI field conditions under any type of insulation material and coating type. Another great benefit of this test method is that it allows for a real-time electrochemical measurements that determine the corrosion rate of the metal, as well as the onset of coating degradation. This is very important in assessing the performance-based conditions of a system under evaluation. The test duration is typically set to 26 weeks or until coating failures occur, whichever comes first. Test assembly. The NACE TG516 test protocol uses coated or uncoated pipe spool that are insulated and placed horizontally in a vessel that contains the electrolyte. To simulate and accelerate the breakdown of the insulation systems, holes are drilled on the bottom of the insulation jacketing. The test method permits for various CUI environments that ranges from isothermal to cyclic operation. For instance, the test method can be used for the following CUI test conditions: within the CUI temperature range defined per the NACE SP0918, within the CUI temperature range but below the dew point, within the CUI temperature range cycling it above or below, and above or below the CUI temperature range, cycling it into it intermittently. Two test setups were used depending on the upper temperature limit. The test assembly shown is commonly used for high temperature environments in the order of 700 to 800 degrees Fahrenheit. The lower temperature, up to 500 F, uses inline pipe spool for practical purposes. For all the cases, the CUI test assembly involves the use of coated or uncoated pipe, a thermal insulation, and a metal sheeting. The test assembly is put together following typical field installation guidelines. This test assembly is equipped with low-profile thermocouples placed on the pipe surface in contact with the insulation. This test setup can also be equipped with wetness sensors to measure the actual duration of the wet-dry cycle events. Low temperature condition. For the low temperature condition, inline pipe spools interconnected with isolation couplings are used. The couplings are used to electrically isolate each of the pipe spools with the purpose of executing the electrochemical measurements. The gap between the couplings and the pipe surface are sealed with silicone to prevent water ingress inside the pipe. Then the pipe spools are insulated with a given thermal insulation wrapped with a metal sheeting following field insulation practices. To attain low temperatures, cold air source is fed on the inside of the pipe using a vortex tube placed on the inlet of the pipe spool. A solenoid valve is installed upstream of the vortex tube to control the airflow. Replacing the cold air by hot air at the source, this test setup can be used to model CUI in the temperature range between 50 degrees Fahrenheit up to 500 degrees Fahrenheit. During this setup, chlorides or other contaminants can be added to determine the effect of these contaminants. Wet-dry cycles are repeated for the duration of the test to accelerate the occurrence of CUI. Cyclic sweating condition. This test apparatus is designed for test temperatures ranging from 50 degrees Fahrenheit to 800 degrees Fahrenheit. This test method uses individual pipe spools that are placed in an individual vessel. A thermal heater rod is placed inside along the inside diameter of the pipe spools to irradiate heat to the inner surface of the pipe spools. The heater rod is placed through connection ports to make sure that the heater is centrally located alongside the pipe. Incoming air can be used instead of heated rod, but there's a maximum temperature limit with the use of blown hot air inside. The measurement sequence, additions of contaminants, and time of exposures is comparable to that of the low temperature condition. Again, wet, dry, and hot-cold cycles are used to accelerate the occurrence of CUI. For this test setup, the pipe spool is sandwiched between two metal plates using threaded rods. Quartz and graphite gaskets are placed at both ends of the pipe to electrically isolate the pipe from the metal enclosure. Analysis techniques. For the in-situ electrochemical measurements, a reference electrode is placed outside the jacket in contact with the external solution. The metal jacket is used as a counter electrode. Typical electrochemical measurements include open circuit potentials, linear polarization resistance, and electrochemical impedance spectroscopy. These techniques have been successful in tracking corrosion rates and coating integrity under insulation in real time. For the electrochemical impedance spectroscopy, equivalent circuits are used to model the physical behavior of the CUI process. Other analysis methods are conducted after the removal of the insulation after a CUI exposure. Visual observation, ultrasonic measurements, and optical microscopy are used to determine the surface condition, and the result can be compared to those of the electrochemical measurements. Disclaimer slide. Part of the Institute policy, SwRI Research Institute does not endorse or promote any commercial products, as the Institute is a third-party independent research lab. Having said that, the results, opinions, and conclusions presented next are those of the JM only. I'm going to stop my talk at this time and let Ames continue with his part of the talk. Thank you.
Thanks, Leo, for that introduction. Before I deep dive into the technical part of my presentation, I wanted to give some background on why JM initiated this project with SwRI. Over the years, speaking with contractors, owners, and engineers, one question that always came up is how our installations behave in field conditions. The problem with that question is that there's so little data, or at least public data, shared by end users on the topic. So to really get a good understanding, you need to know all the conditions and variables to evaluate the system. So not only the installation materials, but conditions, including the presence of coatings, if there are any, type of pipe, environmental exposures, time in service, and even special circumstances like obvious damage or water intrusion. So that being said, a couple of years ago, we were speaking with ExxonMobil, and they suggested we look at a test being co-developed by them and SwRI. Again, this is the test that Leo just described. What made the test method really intriguing to us is that ExxonMobil stated that the test had been field validated and that the results, the testing agreed very well with what they've seen in the process, again, kind of what Leo has just mentioned. So with the background, we decided to evaluate the NACE test method with the objectives of not only evaluating our installation products, but also the test method itself. In this webinar, I'm going to discuss the testing completed to evaluate the two conditions that Leo introduced. We looked at two insulation blankets as well as the impact of thermal spray aluminum coatings on CUI. And because we're insulation manufacturers, we wanted to expand and develop the test to investigate the impact of long-term accelerated conditions on the thermal performance of installations. Second, we know the industry uses laboratory scale CUI tests such as ASTM C665 and C1617 to evaluate materials. Johns Manville uses the same test methods, and all the results are noted on our data pages as well as our competitors' product data pages. So one of the goals for this study was to see how NACE TG516 compares to results from laboratory scale tests. We want to make sure that tests we are conducting are representative of what our customers are seeing in the field and not just another data point. Finally, the main objective is to really provide our customers and the industry the information they need to make decisions. Again, we want to provide our data for the customers so they actually can use it and relate to, and that it's just another data point that may or may not be relevant to their application. So for the following study, we focused on two blanket installations. First is a microporous blanket that JM launched in 2014, Insulthin HT, and the second is a silica aerogel blanket that is currently available in the market. Both are blankets and both are hydrophobic, so we and the people we consulted felt that these products were a good comparison of what was going to be, our or JM's first study of this test protocol. So to begin, and so that everybody's clear on the details of the conditions that were tested, the first set of data that I'm going to be talking about is what Leo referred to as the low temperature conditions. So this profile kept the pipe between 40 and 60 degrees F during the entire 6-month test protocol. So in this manner, the installation and assembly remained wet the entire time. Each day, the sample setups were filled with water in the morning and then drained at night. One thing that's really important to point out is that for the first 2 months, tap water was used to fill the chamber, as can be seen in the top right picture, and in the last 4 months, a 1500 ppm chloride solution was used to further accelerate the condition of corrosion under insulation. This first slide shows results from the electrochemical method that Leo described earlier under the low temperature sweating conditions. So SwRI calculated the mean corrosion rates in situ throughout the 6-month time frame for each installation, and they're shown in the table on the bottom of the slide. The pictures taken by SwRI after the installation was removed from the carbon steel specimens are also shown on the top portion of the slide. The carbon steel pipe specimens were pressure washed to remove most of the corrosion byproducts, and you can see that both pipe sections look very similar with some corrosion affected areas, but otherwise the sections look fairly uniform. Keep in mind that the pictures are representative of the carbon steel pipes after exposure to both the 2 months of tap water and the 4 months of 15 ppm chloride. So looking at the data table, the electrochemical test methods confirm that the mean corrosion depths for each installation were very similar. And based on SwRI's historical data and expertise, the depths were statistically the same for both of the installations at the 2 different time periods. Another way we looked at the samples was using the ultrasonic test method, and what we saw was the results depicted the same conclusions as the electrochemical methods. Shown here are the localized measurements of actual pipe thicknesses after a 6-month test. Keep in mind that the ultrasonic test method can only be taken after the assembly has been taken apart and the insulation blanket removed. So how this works is the ultrasonic test method measures different areas of the pipe section's remaining thickness after the corrosion test period. The initial thickness of the pipe sections was about the same at 0.205 inches, and both pipes had a minimum post-test wall thickness of 0.194 inches. So if you do the math by subtracting the minimum post-test wall thickness, which is in that second column, from the initial wall thickness, which is in the first column, you can calculate that the maximum pitting depth is compared in the third column. And what we see is that the ultrasonic method, with both pipes, they were statistically the same in regards to corrosion pitting. That is, the corrosion resulted in about 5% loss in wall thickness at these localized points after the sweating conditions. So I want to reiterate before we leave the slide that the numbers of this table are localized corrosion depths as opposed to the mean corrosion depths that the electrochemical method calculates in the previous slide. That's one of the reasons why I kept the units different in presenting the information, essentially to act as a differentiation between the two different test methods, being the electrochemical and the ultrasonic. So next we wanted to describe the impact of cyclic and sweating conditions on the 2 installation assemblies. One assembly with the Insulthin and the other with the silica aerogel blanket. Here the same filling and the draining of the water was conducted, but now the introduction of a 600-degree Fahrenheit condition was explored. Each week, 2 cycles of high temperature conditions were exposed to the samples. So there were times when the assemblies was actually dry, unlike the sweating condition when it is wet the entire 6-month time frame. And what we're mimicking with the Cyclic test is repeated cycles of startups and shutdowns in the field conditions. So So following the same analysis as the cold sweating conditions that I've already shared, shown in this slide are pictures of the samples after a good high pressure wash to remove the corrosion byproducts. The table below again depicts the mean corrosion depth after the 2 months of tap water exposure and then the 4 months of chloride solution exposure. So what we see is, unlike the sweating conditions, you can clearly see that in both pictures and the data in the table that the insult-thin blanket has a much lower corrosion rate than the silica aerogel blanket. The data in the table shows an order of magnitude difference in the mean corrosion depth after both the solution exposures and times. So after the 2 months of tap water exposure, the mean corrosion depth difference was 7 microns for the insult-thin versus 91 for the aerogel blanket. This difference increased to 213 microns for the insult-thin and almost 1,400 microns for the aerogel blanket after the 4 months of 1,500 ppm chloride exposure. The difference in corrosion depth is also seen in the pictures where the silica aerogel blanket has much more corrosion pitting on the surface of pipe than the insult-thin blanket specimens. So what this shows is that by changing the condition of the test environment, or in actuality, the process conditions, you can get a very large difference in the CUI results. In this example, the insulation makes also a difference, but so does the cyclic heating of the pipes. If we look at the samples using the ultrasonic method, the same conclusions can be made, which is comforting that both methods show the same results. If we do the math again as we did earlier, in the third column we see that the maximum pitting depth of the insult-thin sample is lower than the silica aerogel blanket. And what this means is that the insult-thin blanket, or the sample, has more metal remaining after the test period. Taking it a step further, what this really shows is that not only is the mean corrosion depth higher for the silica aerogel blanket, as calculated by the electrochemical method, but more importantly, the ultrasonic method can really see the presence of the critical deep pitting that can lead to failures. And it's really these localized pits that are the areas of most concern because they're harder to detect and usually where the failures occur. SwRI also took some cross-sections and analyzed the pipe samples using optical microscopy. Again, the presence of deep corrosion pits were evident in the silica aerogel blanket more than the insult-thin HT. In the microscopy images on the slide, you can see that the dark areas where the blue arrows are pointed show the presence of the pits in the pictures. And though both insulation samples show the presence of corrosion pits of varying depths, the silica aerogel blankets were clearly much deeper and wider than the insult-thin samples at the various points that we looked at. So this is the third piece of data that really confirms that the silica aerogel blanket has deeper pits at the accelerated sweating and cyclic high temperature conditions. The second objective of our study was to compare the results of the NACE TG516 test protocol with the accepted ASTM methods that we've used for evaluating corrosion in the past. In particular, ASTM C665, which has been around for decades, and the new C1617 test method that was developed and has been used over the last 5+ years. The C665 test method is more qualitative in nature and compares the amount of corrosion using a visual inspection after sandwiching a piece of carbon steel between two insulation pieces and exposing it to about 90 degrees Fahrenheit and 90% humidity for 96 hours. C1617, on the other hand, uses a quantitative process and it compares the mass loss when a leachate solution made from the insulations are dripped onto a carbon steel coupon and dried repeatedly again for about 96 hours. So very encouragingly, the results of both the ASTM test methods agree with what we've seen and what we just described in the NACE TG 516 protocol. And you can see that the silica aerogel blanket has more visible corrosion products on the surface compared to the insult-thin HT sample using the ASTM C665, and that the mass loss corrosion rate in C1617 is 4 times higher in the silica aerogel blanket compared to the insult-thin. The last corrosion-based analysis that we conducted compared the impact of TSA, or thermal spray aluminum coatings, using the NACE TG516 test protocol. So we only looked at this with insult-thin that was coated with TSA coatings and applied to the pipe before installing the insulation and not the silica aerogel blanket. So we can see on the bottom left-hand corner picture is a nice TSA coating on a section of the pipe from a sample of the tested specimen. The table shown in this slide is split to show the results of both environmental conditions, both the cold sweating and the hot cyclic. Also shown in the table is a comparison between the mean corrosion depth with and without the TSA coating after both the 2-month exposure to tap water and the 4-month exposure to 15 ppm chloride. In all conditions, you can see that the TSA decreases the mean corrosion depth by at least an order of magnitude, and this isn't really surprising since that is what the TSA is supposed to do, but it's also an example of how this test method can be used to explore the impact of not only insulations that we've done earlier in the study, but also the coatings in the full insulation systems. So switching now to the impact of real-world accelerated corrosion conditions to insulation thermal performance, what we did is we evaluated the thermal performance of both insulations at different times. You can see in this table that we looked at it from a perspective of 1 week, 3 months, and 6 months. How we did this is we placed a thermocouple at the outside of the sheathing in the high temperature cyclic assembly and measured the temperatures when the pipe was at its 600-degree time cycle. So you can see that throughout the test period, the insulation blanket provides more insulating value compared to the silica aerogel blanket. And this is to be expected based on the theoretical thermal conductivity values and test conditions as calculated by the NAMA's 3+ program that we've shown here on the far right side of the table for each of the insulation blankets. However, the one thing that's interesting is the silica aerogel blanket looks to have a thermal degradation performance over time that's more accelerated than the insulation blanket. So for example, at the 1 week mark, the temperature difference is 19 degrees Fahrenheit between the two insulations. You can see the 177 for the aerogel and 158 for the insulation. But after the 6-month test period, the difference increased to 27 degrees Fahrenheit. You can also see there at 191 for the aerogel and 164 for the insulation. In addition, the temperature difference between the actual and theoretical expected values increased for the aerogel from 8 degrees to 22 degrees over the 6-month time frame, while the increase was only 4 degrees for the insulation HT. To address some of the thermal degradation differences that I just presented between the two different blanket installations, what we did is we reviewed the thermal conductivity data produced from a third party using ASTM-C335, which uses a round geometry as opposed to flat. It's important to note that the round geometry thermal conductivity data is much more representative for pipes. This is what we used here, using the actual process compared to the flat thermal conductivity data. The data shows that some of the thermal degradation seen in the previous slide can be partially explained by a thermal shift phenomenon that we've seen with silica aerogel blankets, but not the micropore-based blankets like insulation. To briefly summarize, exposing silica aerogels to high temperatures results in a degradation in aerogel structure and therefore thermal performance. And this can be seen in the difference between the two lines in the graph comparing the first and the second cycles on the graph on this slide. The first cycle is data from virgin product not exposed to heat, and the second cycle is a repeat of the same material exposed to a mean temperature of about 700 degrees Fahrenheit. The first and second cycle lines are right on top of each other for the insulation, meaning that the temperature does not really affect the thermal performance, but with the aerogel you can see a 20 to 30% higher values on the second cycle compared to the first cycle. So the thermal shift can explain part of the difference between the thermal test data that, again, we've shown in the previous slide, but we also know that the presence of water can affect the thermal performance to varying degrees of most insulation materials. So to summarize, the conclusions from this third-party study completed SwRI are the following. First, at the low temperature sweating conditions, insulation and HT and silica aerogels have similar corrosion rates and depths, and this was seen in both the electrochemical and ultrasonic test methods. At high temperature cycling conditions, insulation has a lower corrosion rate and depth compared to silica aerogels, and more importantly, the silica aerogel causes deeper localized pitch, which again is very significant from a failure analysis standpoint compared to a uniform surface corrosion. Third, our analysis of a TSA coating showed it can reduce the amount of corrosion, and that this NACE test method that we just reviewed can be used not only for looking at insulation materials but also coatings. Fourth, based on some add-on testing that we did to complete the understanding of the thermal performance of the two different installations after the corrosion, with accelerated corrosion conditions, we confirmed the presence of a thermal shift with the silica aerogel blanket, but not the insul-thin at the wet and high temperature exposures. And finally, from an insulation manufacturer standpoint, one of the important learnings for us from this study was the conclusion that there's pretty good conclusion between the laboratory scale testing that we've been doing that are on our data pages, the C1617 and C665, and the system testing, again, that we just described here in the NACE TG516. And even more critical, as Leo described, that there's pretty good agreement between the NACE test method and field conditions as seen by ExxonMobil and the collaboration with them. So to conclude the presentation portion of the webinar, Leo will be speaking to some future programs at Southwest Research Institute and NACE. Leo?
Thanks, Ames, for the technical background. SwRI Joint Industry Program. So I'm going to take advantage of this venue to let you know that we are assembling a joint industry program on corrosion under insulation. A JIP launch meeting was held in Houston on May 16th at the ExxonMobil campus. A total of 20 companies attended the meeting. I'm going to list a few takeaways of the joint industry program that pertains to the operators and vendors, as well as service companies. From the operator's point of view, this joint industry program will provide guidance on better inspection intervals on CUI components, better selection of coating insulation systems, limits of the operability of coatings and insulation, and the effect of the service environment on coating life and insulation type. Now, from the coating and insulation manufacturer's point of view, this joint industry program will provide guidance on more accurate prediction of long-term performance of coatings and insulation, as well as support new coatings and insulation development. With that, we finish the technical background with the presentation and revert back to you, Kim, for a final wrap-up. Thank you.
Great. Thank you so much, Leo. Ames, if you could go ahead and go forward to the next slide. So for everybody who attended the live webinar today, you'll receive a certificate of completion following the webinar, and that'll be sent to you by Friday. And then moving on, if you found this webinar useful today, I wanted to talk briefly about some of the other technical information we have and additional resources that we have available for you. The first is our webinar schedule, and this is a schedule of all the webinars we'll have this year for the industrial, mechanical, and HVAC markets. As you know, you can't always attend, as we know, you can't always attend a live webinar, and so we record each of our webinars and post them on our exclusive content portal of our website. Now, this is where you can find each of our webinars, as well as videos, white papers, and additional technical documentation that you may find useful for future reference. We also offer what's called an engineer's portal, and this is currently available for our mechanical and HVAC products. And it basically aggregates the detailed technical information for each of our products in a single location. And then finally, we also regularly publish blogs that we've written by JM technical experts, as well as experts throughout the industry. And these blogs really hit on targeted technical information, the latest news in the industry, and scientific details that are really critical to a successful insulation system design and operation. And so as we conclude that, we'll go ahead and move on to our questions. Now, the first question we got today is for Leo, and that is, can you define field validation and how this has been completed?
Thanks, Kim. Yes, the field validation was performed during the execution of the ExxonMobil programs, and ExxonMobil validated the results of the investigation of the lab CUI investigation with field data that they have collected. So the field validation was one big item in terms of validating the test methods that was developed as part of the ExxonMobil programs here at Southwest.
All right, great. It looks like the next one is for you as well, and that is, have you tested any other insulating materials via this new test method?
I can comment on a few items that were part of the initial program. There were a lot of products that were part of the initial testing: mineral wool, cellular glass, PIR, several insulation materials that were used as part of the initial testing, as well as TSA and numerous coatings that were provided for the initial development of the program, and those were selected by ExxonMobil as part of the program development.
Great, thank you. Ames, the next one is for you, and that is, are there any other corrosion inhibitors in the blankets discussed today?
So there aren't any advertised inhibitors in either the Insulthin or the Silica aerogel blanket. And that being said, JM does have two other products that have corrosion inhibitors, which we call XOX, and that's our Thermo 12 Gold calcium silicate as well as our Sprule Perlite products. And both of these products have been tested via the ASTM-C1617 that I mentioned during the webinar. And what it showed is that the leachate solutions from both of those products, the calcium and the perlite, have less corrosion when compared to deionized water.
All right, thank you. Leo, this one's coming to you, and that is, what other testing has been completed with this protocol? Different metals, different metal pipes, coatings, or insulations?
Yes, and as I mentioned before, this was the Exxon program that looked at different insulation materials, such as mineral wool, PIR, cellular glass, and some others that are included in part of the testing, as well as TSA and some other coatings that ExxonMobil needed to validate against the field data that they had.
All right, great. Leo, this one's for you again as well. Does CUI have different mechanisms in different parts of the world?
Well, the ultimate consequence of CUI is corrosion of the pipe or the equipment underneath the insulation. And indeed, the corrosion rate or the degradation will certainly depend on the environmental conditions and the climate that this equipment is being exposed to. Acid rain in some parts of the world may have a completely different end result as opposed to an industrial scenario. Marine environments or industries that are located near a marine area, marine coastal area, will certainly have a different degradation rate as you would normally see in inline industry. So certainly climate plays a big role around the world in terms of the acceleration of CUI.
All right, great. Ames, this one's for you, and that is, what is the thickness of insulations used in the test assembly?
So we use 2 layers of 10-millimeter blanket for the high temperature cyclic conditions, and then 2 layers of 5-millimeter blankets for the low temperature sweating conditions. And those thicknesses were used for both the Insulthin and the aerogel blanket.
Great. So Leo, what is the effect of pH on corrosion?
pH, as you probably relate to the environmental conditions around the pipe, will have a significant effect on the corrosion rate of bare metal, and in some cases, to some extent, to coating degradation. High pH in carbon steel may have a passivating effect, whereas high pH, greater than 9, on TSA may imply that the aluminum can corrode at much faster rate than if the pH is lower than 9. So certainly pH has an effect on the corrosion rate depending on which metal you are using, and of course the coating type that is being employed under insulation.
All right. Ames, can you speak to the hydrophobic properties of the blankets and whether or not they disappear over time?
So yes, depending on the time and temperature and exposure, at about 450 degrees, the chemicals that give the blankets their hydrophobic properties start to oxidize, and therefore at that time, depending on the duration, the hydrophobic properties of the blankets are reduced. But if you think about it from a pipe standpoint, if the pipe is what is hot, you're going to have that inner layer of the blanket probably lose its hydrophobic properties before the outer layer.
Great. Leo, so the next question is for you, and that is, can you vary the test protocol in assembly? What is the status of NACE 516 being accepted?
Yes, the test protocol can be can be adapted to the customer's need. The test specimen size can be also varied, as well as the type of insulation that is used and the number of layers of insulation that is used, all based on customer's need. The cyclic events, there are certain items in the test that are required to be constant or as set in the standard, but some others can be tweaked based on the customer requirements. Now, in the status of the NACE TG 516 being accepted by the NACE, right now we are on the second draft of the document after receiving a few comments on the original draft, and that's moving along. So I don't have a real timeline on the status of the final document, but certainly it is being produced at this moment.
Okay. The next one's for you as well, and that is, can you explain why the low temperature test is considered sweating when the assembly is actually immersed in water?
Yes, the low temperature or sweating case is being designed to reproduce dew point conditions in which you have a pipe, a wet pipe condition at all times. Now, the presence of external solution can be associated with for instance, a rain event in the field in which you have a full saturation of the pipe. So you have a sweating condition on top of a full immersion or full saturation of the insulation. So that's why the sweating condition and the wet events are being thought in the test protocol.
Great. Ames, the next one is for you, and it is, are there chlorides in the blankets?
So one way to answer that question is based on ASTM C871, which we use is to analyze the leachable chlorides, fluorides, and silicon sodiums. There are chlorides detected, and we've done both blankets, and there are some on both. That being said, if you use ASTM C795, both blankets fall in the acceptable range for the insulation materials for use with austenitic stainless steel.
Great. So Leo, and that is, the next question is, will ASTM be accepting this test method?
Yes, as part of the NACE technical committee, TG 516, yes, this standard test method will be accepted by the NACE community as the recommended practice for testing CUI in the laboratory.
So this question actually referred to ASTM and not NACE?
Oh, yes. There hasn't been any approach by ASTM or us to the ASTM community, but certainly that's an option after the final approval by NACE. So yes, there could be future communications with the ASTM community to see how these tests can be employed and adopted as a standard practice for CUI evaluation within ASTM.
Great. And the next one, the final question is, what role did the hydrophobicity play in the testing? Sorry, Leo, that one's for you.
Yes, the hydrophobicity, we have not tested it primarily as a hydrophobic insulation as part of the test protocol. Presumably, the hydrophobicity of the insulation plays a role in terms of the water being accumulated once the wet event takes place, but indirectly measuring corrosion rate and also the properties or condition after the insulation is removed. The hydrophobicity of the insulation will play a role in the ultimate corrosion rate of the system of the pipe. So yes, there could be a factor in terms of the hydrophobicity affecting the cyclic event and the ultimate wet conditions at the gap between the pipe and the insulation.
Excellent, thank you. Well, that concludes our presentation and our questions for today. So you will receive a survey following this webinar, and we would appreciate if you take a little time to offer your feedback on the webinar today. If you have any questions that you weren't able to ask, you can actually submit them via the survey, and we'll respond to you directly via email. Now, please keep an eye out on your inbox for your certificate of completion, and that's going to be sent to you, as I said, by Friday. Now, we will also be posting a recording of this webinar online, so if you missed any part of our presentation or if you'd like to view it a second time, you'll certainly be able to access that on our website in the exclusive content portal. Otherwise, thank you for attending today, and we hope you enjoy the rest of your week.